The video recording is on. Hello everyone. Welcome back to our channel. And we are looking at the seventh experiment. We are done with the six experiments, five are lab view. Now we are starting with MATLAB. So the seventh experiment goes to the response for of second order system for unit step input. This is a starting. This is a block. Last time I in the six experiments I let you know what were the things inside these blocks. There is a detailed video. We won't be going into those details right now. We are going only for the seventh experiment. That is for the second order system. The first order system has already been done on the channel. So let's start. So the aim for this is to determine and analyze the unit step response of second order system. We understand this thing by the title of the experiment. And then comes the software. We are, of course, we are using MATLAB as this is a MATLAB series. And the core concept is the most important is that there is a damping ratio. Okay, zeta. It's called zeta. Okay. I don't have it right now, but I'll let you know. So it's called zeta. It's signed like this. The value of zeta completely changes the shape of the response graph. This experiment analyzes the four possible cases of zeta. Okay, the key procedure, the story. Okay, so this experiment analyzes the step response of second order system. The standard transfer function is the omega square n by s square plus s zeta omega ns plus omega square n. The entire behavior of the system depends on the value of the damping ratio, that is zeta. So at every point, okay, so here you can see there are four things. So for example, if this is the first case, at this case, when zeta is 0, we have a sine-like graph. Okay, okay. So at this case, we have a sine-like graph when the zeta is underdamped. System has no damping. The response is continuous, pure oscillation that never settles down or stops. This is never settling down or stopping. The same thing is here, and at certain point it's going up, it's going down, it's again going up, and at certain point it will get you know constant. Okay, so at that constant point, so what we are doing in this is we are giving the zeta value between 0 and 1. So this is the 0, this is your 0.9 or 1, you can take it as a case, because the zeta value should be less than 0 for underdamped. This is undamped. The other we saw was this was undamped. This is underdamped. Okay. So under damped, this is a very common case. The system is damped, but not completely. It still oscillates. At certain point, it will get constant, but there at every constant, even if it gets, it won't be like a straight line. There will be some ripples around it. It will be small, not visible, but there would be in the mathematical notations. Okay, and then we go on the third case. The third case itself we can see is when zeta is equal to 1. As you go, you just need to change the values in this box. That is the zeta value. That is the denominator value. As the denominator value changes, our system graph changes. Okay, so when zeta is equals to 1, the system we call it as critically damped. This is a perfect amount of damping. It has a perfect curvature, and it starts from 0 till 1. It is very perfect, and the response rises to the final value as fast as possible without any overshoot or oscillations at all. Okay, so last three times what was happening was it was going up, it was again coming down till 0, it was again overshoot, there was shoot, undershoot, overshoot, undershoot. It was going up and down. There were oscillations. Right now we got the output without the oscillation because our zeta was equals to 1, and because of that it is called a perfect damping. Okay, the fourth we see is the fourth case, that is zeta should be greater than 1, that is overdamped. This system has too much damping. Okay, this response is very slow and sluggish. It also has no overshoot, but it takes much longer to reach the final critically damped case. Okay, so when it is greater than 0, okay, so it is going above at 0.6. At that point you can place it as middle point kind of thing. So and from here to the 1 point, it will take much more time than the critically damped thing. Okay, from 0 to 0.6. This is the middle point, you can say. And from 0.6 to the 1, it is very slow compared to that of the perfectly damped oscillation, or when oscillation is when zeta is equal to 1, or critically damped system, which we call it. And I think so that's all for this video we have been looking for. The seventh experiment is now completed. In this series, there are more 5 experiments yet to be come, and 6 experiments we have already done. This is the seventh experiment we have done right now. Yeah, thank you. Keep watching.